Today we'll take up the concept of electric potential and moving from there to potential difference. Traditionally, in textbooks, we usually, after discussing the idea of charge, we usually go into electric current. I feel that it's not a good idea to go into electric current after discussing charge. It seems to make more sense to think in terms of what is electric potential, and then to work out what is potential difference, and then to come to the idea of an electric current as the flow of charge from one point to another. So if you don't understand why the charge is flowing, I think talking about current would be a little premature. So to discuss electric potential, the fundamental ideas that we need to know, which should have been covered by now in class 9, is that the concept of a charge. What is a charge? It is usually represented by the symbols Q, large, capital Q for a large charge, and usually a small q for a smaller charge. I have seen both being used, so I'm putting both out there, but generally you will see the small q. So what do we know about charges? Charges can be positive or negative. So there is a kind of historical narrative of how we came to find that out. Do look that up. The positive and negative charges relate to the fact that fundamental particles, the neutron in the nucleus of an atom, and the electrons that are supposedly moving around the nucleus, these are fundamentally opposite to each other in terms of their charge. We have ample experimental evidence for this. Then, since we also observe that these charges apply a force on each other when they are brought brought near each other, then those forces are called electrostatic forces because they come from the fact that they are charged particles. Like particles repel, and rather like particles apply a repulsive force between them, and oppositely charged particles apply a attractive force between them. We know also from experimentation that the charge itself of objects which are charged are quantized. They have a fundamental unit. Please look at the previous video that we made for that. Minus 1.6 times 10 power 19 coulombs per electron is the charge on an electron. That's why I put the negative over here. And of course, the counterpart of it would be plus 1.6 times 10 power minus 19 coulombs per proton. We have already discussed the work of Charles Augustin Coulomb, who found out that the electrostatic forces are governed by a certain equation. And that equation, of course, is the force between any two charges Q1 and Q2 can be found out by multiplying the Coulomb's constant Q1 Q2 upon R square. We have seen an equation that looks very similar. In fact, it's almost exactly the same. Gravitational forces between any two masses M1 M2 can be determined by multiplying the universal gravitational constant divided by the square of the distance between them. So something quite remarkable appears out of these investigations. So from that we move into electric potential. So the way we define electric potential is something like this. This is a little theoretical, and I hope you people will ask enough questions to be clear about it. So you have to follow all the arguments a little closely, okay, and ask a lot of questions. So take a large positive charge. You can keep it as negative also, but traditionally we keep it as a positive, with a charge Q. Okay, so the capital Q represents that it is a very large charge, and place within its vicinity, somewhere in the area around it, a very tiny positive test charge. I hope that rings a bell for you people, because I remember doing this discussion with you in class 9, with you all in class 9. Very small. So the nature of the charges are something like this. Q is very, very large in comparison to small q. Large q is very large in comparison to small q. And there is a reason behind it. I'll come to it in a moment. Now, when this charge is placed at a certain distance from this object, okay, and this distance is your r. Okay, sorry, this has to be parallel to this. That just came out unintentionally like that. Maybe I should change it. I'll do it. Okay, then the small positive test charge is going to experience a force because of the large test charge. So could you answer a simple question? In what direction will the force be experienced? You can answer it by voice. A large positive, sorry?
Towards, like, it's repelling it, so that this
Yeah, so
north, I mean, from what I can see, it's towards the north, and the north,
yeah, so it's repelling it, so
north.
so it will push it away, the force will push it away. So can you put it even more specifically, in what direction will it push it? Okay, yes. So several answers were attempted to talk about in which direction will Q move. So it's obvious, since both are positive charges, that the force is a repulsive force. So Q is going to be pushed in this direction. Okay, so how do you say in this direction to mean it universally? Say for after all, Q need not, this is a two-dimensional plane that I'm showing it. It can be three-dimensional. The charge could be out here. Okay, so the correct way of stating in which direction it will be pushed is, you have to say the force acts radially outward. Okay, so the force with which it's going to be pushed is then going to be acting in this direction with reference to this particular diagram. Okay, and can anybody tell me what is going to be that force? Can you determine that force? The answer, of course, is staring you in the face. But if somebody can answer that question. So yes, of course, the can be determined. It can be determined using Coulomb's equation over here. All you need to know is the value of Q1, Q2, and R and the Coulomb's constant. So if you know that, then you can calculate what is the force with which it is going to be pulled, rather pushed.
Arun, sir?
Yeah, let's call that force F1. Yes, Sonia.
I had just gotten disconnected. What are we talking about?
We are talking about a force Q placed somewhere near Q, large Q. It's going to experience a force in the outward direction. So we call that force acts radially outward, because the same thing will happen wherever you place it around this, it will get pushed out. So you say radially outward. And we said that this force is a finite force, and we can calculate that force by using Coulomb's law. That's all I have said. Okay, is that clear? Now let's say that this positive test charge is pushed, okay, and it is brought closer to Q. So it's no more in that position. I did some work, I worked very hard, I caught hold of the positive Q and I pushed it against the force of repulsion of this large test charge, and I brought it to a new position, let's say somewhere here. So this is the new position of the test charge, and therefore this is the new distance between the two. Okay, and I'll call it what I'll call this as R1, then I can call this as R2. Okay, same test charge, but I pushed it. So I did the work in pushing it from here to here. If you can imagine it like that, if it helps to imagine it like that. So when I pushed it from this place to this place, I did work. How can you say that? Well, you can say that because I pushed it, that means I applied a force, and by using my effort, I moved it by this distance. It is a certain distance d that I moved it by. So the force that I applied, okay, which we need to discuss what that force is, multiplied by this distance is going to tell me the amount of work that I have done to push it from here. Okay, and if this is a little confusing, you can think about the same thing in terms of the analogy for gravity. So if there is an object which is placed at a certain height, that is, it's at 0 to the ground, if you applied an upward force and you lifted it through a certain distance, right, then you have done some work on it. That work will be the force that you applied multiplied by the height, and therefore you get the GPE, the gravitational potential energy of it, that is mgh, right? So you did the work lifting it from here to here, so therefore that work will become the potential energy of this object, the gravitational potential energy of the object at that height. The same analogy applies here. I pushed it from here to here. Only thing is, over here it is a constant force, but over here it's not a constant force, because as I get closer and closer to this Q, the R square, the R will reduce. It's also true here, but that's a different discussion. But the R will reduce, and when the R reduces, the force will become higher. So when I push it from here to here, I'm going to experience larger and larger and larger and larger force. It's going to be harder to get it here than to move it from here, right? So when I get to this point, I'll be experiencing a new force. Which will then be k times q1 q2 divided by r2 square. So over here it will be r1 square, over here it will be r2 square. Okay, so there is an electric potential that the object gains when it goes from here to here. Actually, I shouldn't put it like this, since it's the distance moved by it. I can just show it in this direction. So I've moved it in this direction. Okay, and therefore we can say at this point the object has an electric potential. Just like we can say that the object at this point has a gravitational potential, the object when moved from there to here has an electric potential. And that electric potential will be the amount of work done, and listen carefully over here, okay, the amount of work done not to bring it from this position to this position. It is the amount of work done to bring it from infinity to that position. Okay, so that's a little bit of a hard pill to swallow. You have to think about it a little bit before you get to that, because if I say the electric potential of this object is the amount of work done to bring it from here to here, then that is just a difference in the potential. Okay, it is in comparison to this point. Okay? There is a higher potential here in comparison to this, higher electric potential here in comparison to this. But even over here, it has an electric potential. What is that electric potential? That is the electric potential that it has gained by coming from some infinite position. And I'll tell you why an infinite position. Because the Coulomb's law will be zero. The force applicable between these two charges will be zero only when r tends to infinity. So from zero, it doesn't mean that you actually have to bring it from there to here. And this of course confused me when I studied it in high school. Unfortunately, this is coming to you in 10th standard already. But I feel that without talking about this, there really is no point talking about potential difference. So that's why I explore this at this point of time. So when you bring it from there to here, from infinity to here, you can say that the object has electric potential anywhere on the journey. Okay. If you keep the positive test charge over here, it still has an electric potential over there. Why? Because it is going to experience a force of repulsion from this. So why does it have an electric potential? Well, because some work has been done to bring it from infinity to there. Okay. So in that way, we define electric potential at a point. And of course, now you can actually dismantle the experiment and you can say that at any point around this large object, isometrically, I don't know, you people have in geography you have studied iso points, isomers, and in chemistry, and in terms of what is it, the altitude lines. So the same altitude line. Sorry? Anyway, to continue, at all points along the green dotted area, assuming that that's a circle or a part of a circle with a radius r1. Wherever you place a charge, it will have an electric potential, and its electric potential will be the same as long as the distance is the same from this. And of course, that's true not just in two-dimensional plane, it's three-dimensionally true. You can also move this like this. So it will have the same potential everywhere. And that is for a unknown small test charge. Now the electric potential will be in terms of 1 coulomb. So if you have a 1 coulomb test charge, 1 coulomb charge placed over there, which is actually horribly huge. So nobody talks about charges in terms of coulombs. We usually talk in terms of milli, micro coulombs, and so on. But we define electric potential then as the amount of work required to move 1 coulomb of charge from one position to another position. And that is the electric potential at any point around the charged object.